This is the story of the physicist whose impossible equation could fix quantum computing and why he vanished without a trace in 1938. Enrico Fermi, the man who built the first nuclear reactor, ranked this young Italian alongside Galileo and Newton as one of the greatest scientific minds in human history. His name was Ettore Majorana, and just months after publishing the math that billion-dollar companies are now desperate to prove right, he emptied his bank account, boarded a boat in Naples, and was never seen again. The particle he predicted breaks the known rules of physics, a particle that is its own exact opposite. And right now, companies like Microsoft are pouring billions into proving it exists because it could be the missing piece that makes quantum computers actually work. Here is why this story matters right now, and not just as some dusty chapter in a history textbook. The entire next generation of computing, the machines that will crack encryption, simulate new drugs, and model the climate down to individual molecules, all of it runs into one brutal wall. Quantum computers are insanely fragile. The tiniest vibration, a stray atom, even a slight temperature wobble can destroy the data inside them. Physicists have spent decades searching for a way around that problem, and the single most promising solution traces back to a set of equations scribbled by a man who disappeared on a Mediterranean ferry in 1938. By the end of this video, you will understand what Majorana figured out, why nobody believed him for 80 years, and why the biggest tech companies on the planet are now racing to prove a dead man right. Rome in the early 1930s had one of the most stacked physics labs on the planet. Enrico Fermi had assembled a crew of young researchers at the Via Panisperna Institute, a group that would eventually help build the atomic age. And among them stood Ettore Majorana, the strangest and most gifted of them all. Majorana could run terrifyingly complex calculus entirely inside his head. Colleagues described watching him board a tram in Rome, pull out a cigarette pack, and scribble an equation on the back of it while staring out the window. By the time the tram reached his stop, he had solved a problem that would take other physicists months, and then he would crumple up the cigarette pack and toss it in the trash. He did this constantly. Breakthroughs that his peers would have killed to publish ended up in garbage cans across Rome because Majorana never cared about credit or fame. Physics for him was about one thing only: finding the deepest symmetry hidden inside the universe, and once he found it, the paper trail meant nothing. That obsession with symmetry would define both his greatest discovery and his strangest decision. To understand what Majorana saw, you need to know what the rest of physics looked like in the 1930s. A British physicist named Paul Dirac had just dropped one of the wildest predictions in the history of science. Dirac's math showed that every fundamental particle has an evil twin, a mirror version of itself carrying the opposite electrical charge. An electron has a positron. A proton has an antiproton. And if a particle ever meets its antiparticle, the two destroy each other in a burst of pure energy. Dirac called it antimatter, and within a few years, experimenters actually found the positron in a cloud chamber, which confirmed his prediction and won him the Nobel Prize. The entire physics community accepted one core assumption baked into Dirac's equations. A particle and its antiparticle are always two separate things, matter and its mirror, forever distinct. And that is exactly where Majorana looked at the math and saw something nobody else noticed. Majorana took Dirac's equation and rewrote it from scratch. Where Dirac's version demanded two separate entities, particle and antiparticle, Majorana found a mathematical loophole that allowed a single particle to be both at the same time. One object acting as its own opposite. If this particle ever encountered a copy of itself, the two would annihilate each other, because meeting yourself and meeting your antimatter twin would be the same event. The best way to picture it is with a Mobius strip. Take a normal strip of paper and it has two sides, a top and a bottom, just like matter and antimatter in Dirac's world. Now give it a half twist and glue the ends together. Run your finger along what feels like the outside, and without ever lifting your finger, you end up on the inside. The two sides were never separate to begin with. Majorana published this in a single paper in 1937 and called the hypothetical object a Majorana fermion. The physics world shrugged. Nobody had ever observed a particle behaving that way, and the math looked like a clever trick with no real-world match. Most physicists filed it away as a curiosity and moved on. What nobody expected was that the man himself was about to mirror his own equation. By early 1938, Majorana had become increasingly withdrawn and paranoid. He stopped attending lectures, stopped publishing, and pulled away from everyone who knew him. On March 25th of that year, he sat down and wrote two letters. The first went to his family, asking them not to mourn him. The second went to his department head, apologizing for what he called the sudden disappearance. That same day, Majorana emptied his bank account, walked to the port of Naples, and boarded a ferry to Palermo. When the boat docked in Sicily, he sent a telegram back to Naples saying he had changed his mind and planned to return. A return ticket was purchased. The ferry sailed back across the strait. Majorana never got off the boat. Italian police launched a massive search. Mussolini himself ordered the investigation, which turned up nothing. No body, no confirmed sighting, no explanation that made sense. Some investigators concluded he jumped overboard. Others claimed credible witnesses spotted him years later in Argentina, living as a monk. A few theorists even suggested he faked his death to avoid working on nuclear weapons, sensing what Fermi's research would eventually become. The truth is that nobody knows. Ettore Majorana existed in two states at once, alive and dead, leaving and returning, present and absent, and the case has never been closed. Just like the particle he predicted, the man himself became something that could not be resolved. For decades after his disappearance, the Majorana fermion sat in textbooks as a footnote, a neat piece of theoretical math that most physicists respected but nobody had any way to use. That changed when quantum computing moved from blackboard theory to actual engineering. Here is the core problem that every quantum computer faces. Classical computers store information as bits, ones and zeros, and those bits are stable. You can unplug your laptop, drop it on the floor, and the data survives. Quantum computers use qubits, which can exist as 1 and 0 simultaneously, and that power is exactly what makes them so fragile. A qubit's data depends on its quantum state, and the slightest environmental noise, a vibration, a temperature fluctuation of a fraction of a degree, can knock it out of alignment and destroy the information. Engineers call this decoherence, and it is the single biggest obstacle standing between us and useful quantum machines. And this is where Majorana's ghost walked back into the room. In the early 2000s, physicists realized that a Majorana fermion, if it could be created in a controlled lab environment, would solve the decoherence problem entirely. Because the particle is its own antiparticle, you can split a single piece of quantum information across two Majorana particles separated in space. The data is no longer stored in one fragile spot. The information lives in the relationship between the two particles, and that relationship is what physicists call topologically protected. You can bump it, heat it, shake the entire system, and the encoded data survives because you would need to disturb both particles simultaneously to break the code. Microsoft built an entire quantum computing strategy around this idea. Their approach, called topological quantum computing, depends on manufacturing Majorana fermions inside specially designed nanowires cooled to near absolute zero. If it works, these machines would be orders of magnitude more stable than anything Google or IBM has built so far. The catch is that we still have not definitively proven the Majorana fermion exists. Every few years, a research team announces they have detected its signature inside a nanowire. And every few years, the results get challenged, debated, or retracted. A major paper from a Dutch research group in 2018 claimed clear evidence of Majorana particles, and that paper was later withdrawn after other labs could not reproduce the findings. Billions of dollars and entire corporate research divisions now ride on proving that a reclusive Italian genius was right about a scrap of math he published 87 years ago. The greatest technological race of this century depends on a phantom particle dreamed up by a man who treated his own life like an equation that needed to balance out to zero. If Majorana's fermion is ever confirmed, the computers it enables will be powerful enough to simulate entire biological systems, crack every encryption standard in use today, and model problems that classical machines would need longer than the age of the universe to solve. All of that from a single paper written by a man who couldn't be bothered to save his own notes from the garbage. So that's all for today. Thank you so much for watching, and don't forget to subscribe for more videos like this.